right? So the easy way to do that is to look down in the aromatic region, right? So here's our aromatic peak, right? It's a peak that's called a multiplet, so there's a bunch of things going on in that peak. But the most important point is that it integrates to 4, right? That tells you have 4 protons coming off the benzene ring, right? Really important. So we have a di-substituted benzene, all right? So don't worry about the neighboring protons for this, it doesn't matter. The key for our fragment is this is a di-substituted benzene, all right? And if you think about it, there are 3 different ways you can have a di-substituted benzene, all right? You can have it substituted like this, which is called ortho. You can have it substituted like that, which is called meta, or you can have it substituted like that, which is called para. All right, and I write those squiggly lines at the end of the bonds just to denote we're not sure what's there. All right, right now we're not sure what's there, but we know that it's not a proton. All right, so we have one of these, right, and you can think about how we can determine which one we have, right? But that's a really important point. All right, so we know we have this fragment. All right, we also know that we have this fragment. Right, so we just have to figure out what's going on with those 2 carbons, and then we'll be done. Right, so we look down here at the broad singlet, number of neighbors, we don't know. This is our NH2 fragment. Okay, and so we just have these final 2 peaks, right? And so let's interpret those. So 2.5, it integrates to 2. And so if it integrates to 2, we know that that is more than likely going to be a CH2 group. So I'm just going to write down CH2 for the fragment. And I haven't even looked at the multiplicity yet. We'll get to that. 1.3 integrates to 3. So I'm going to write down that that's a CH3. Again, more than likely, when you have something that integrates to 3, it's a CH3. Integrates to 2, it's a CH2. Right? So now let's look at the multiplicity. Right? So when we look at the multiplicity, we can see that we have a quartet, right? Remember the n+1 rule, right? So we're thinking about this, the n+1 rule. We're solving for n for the number of neighbors. So if you have a quartet, that means that you have 4 peaks coming off of that 1 peak. And that means you're going to have 3 neighbors, right? Because 3 goes in here, number of lines you get is 3 plus 1, which is 4, right? The triplet n+1 means we have 2 neighbors. Right, and so when we're thinking about this, we have 3 neighbors next to the CH2, so that means it's going to be next to a CH3. We have 2 neighbors next to the CH3, that means it's going to be a CH2. Hopefully it's clear that this CH2 is that CH2, this CH3 is that CH3. Right, so the fragment that we have is just an ethyl group. Okay. So the fragments we have to bring together is something going on with this benzene ring, an NH2, and a CH2, CH3. Okay? So you have these 3 fragments. How are you going to put them together? I'm going to leave for you to think about how you would pick one of these substitution patterns. I'm just going to randomly pick the ortho and say if we know that it's a di-substituted benzene, there's a structure that's consistent with what we've been talking about. Okay? So think about whether it makes more sense to have it ortho, meta, or para, depending on how the protons are going to show up in these. Right? Think about if symmetry is involved, those sorts of things. Right? But I think this is a really nice structure. Right? Now what we want to do is go back and verify that this is going to make sense. So let's draw this out. We're going to draw it out twice. And let's see if we can place the peaks from the carbon-13 and the proton NMR. So for the carbon-13, that's going to be 25, that's going to be 14. 25 is a little bit more downfield, right? Lower electron density because it's next to the benzene ring. The carbons in the benzene ring are going to be all the ones up here. We're not going to really worry about where they are, so we'll just write it something like this. So that all 6 of those peaks are coming from the benzene ring. That's fine. So we've written out that this is consistent with the carbon NMR. And again, the key point is that there's no symmetry in that structure. The proton NMR, again, this is going to be the multiplet from 7.2 to 6.6, right? And that's going to be our 4H multiplet, right? We're going to have the amine protons at 3.5, right? And that's our 2H broad singlet. And then we have the ethyl group. So this is going to be the 1.3 3H triplet, and then the CH2 is going to be the 2.5 2H quartet, right? And so this is the strategy that I hope you'll use all the time when you're going about doing these structure determination problems. Work from the molecular formula, think about potential structural subunits, go to the IR, make sure that you can figure out what functional groups are present, verify those functional groups by looking quickly at the proton and the carbon NMR. Look to the carbon NMR, see if there's any symmetry, see if it tells you any more about functional groups that are present. Then really dig into the proton NMR. Try to figure out what that's telling you about CH2, CH3, CH. Is it next to an electronegative element? What fragments do you have? Then finally start putting the fragments together. And don't be afraid to put the fragments together in a couple of different ways and figure out which one is more consistent with the data that you have. Always make sure you do this assignment at the end to make sure that it makes sense, right? One thing that you can think about, and I'll let you think about this, is how could we tell that that structure does not work, right? That does not fit, right? So think about how you could show that that is not consistent with the spectral data that we have. We'll continue to practice this on homework and in class. And again, I hope watching me go through this is helpful as you try to improve your structure determination skills.